Thank you. So I would like to talk about applying wavelet theory to the problem of private inference with large language models in AI. We want to do private inference because we want to hide both the model weights, but also, most importantly, the user inputs. So private ML is a huge space. It would be really hard to fit on one slide all the work that has been done. So here we're focusing mostly on MPC protocols based on linear secret sharing, and leaving other type of flavors of MPC aside. But I think it's fair to say in general that there's been a lot of progress being made in the last 4 to 5 years. We've gone all the way from very simple models with a few thousand parameters to really complex large language models with complex architectures, GPT-2, with billions of parameters. And dealing with large language models is really tricky with MPC because they have nonlinearities which are hard to handle. They're not just like ReLU, which is easy to model with just one comparison, but they're more complex. They are like GLU and they are more nuanced. And so you have one group of papers and protocols that sacrifice performance and model accuracy in favor of simplicity. But you have another group which is very interesting, including Iron, Krypton, and Sigma, which really achieve really good precision in terms of modeling those nonlinearities, and therefore don't sacrifice on model accuracy. And for example, Sigma is able to run inference on a 1.3 billion parameter model, GPT-2, in under 10 seconds per token. It's pretty impressive. Therefore, the bottleneck is really in the nonlinearities, in these complex nonlinearities. And for example, here we have some of them, like GLU and so on. And typically, the way to go about this is by using function secret sharing, which is very efficient in terms of round complexity, but also in terms of communication complexity, to the extent that it actually shifts the problem to computational complexity. And therefore, many of these protocols provide versions for GPU, optimized for GPU. So we're going to try and address the bottleneck of computational complexity that we find when we use function secret sharing by looking at it from the perspective of theory that is well known in the realm of digital signal processing. It's called wavelet theory. And in particular, one tool that it has that is called multi-resolution analysis. So it's a distant cousin of discrete Fourier transform, the discrete wavelet transform. There's a linear transformation, but there's a couple of differences. One is that you don't have just one set of basis functions. You actually may have several ones, which are called wavelet families. And also those basis functions are, they have a finite support, meaning that they're non-zero in only a finite interval. And they're very efficient actually to compute, more efficient than discrete wavelet transform. So this is a beautiful mathematical structure, the multi-resolution analysis. And the idea is that you have a signal living in a vector space, and then you create this structure of nested subspaces that provide less and less resolution. So you project your signal onto those subspaces, losing information from your signal, making it more coarse. It's like zooming out from a picture, losing information, making it more blurry. But at the same time, you have this other structure on the right-hand side that captures all the details, all the information that you lost when going from one approximation subspace into the next one. So altogether, no information is lost in this picture. And the way to picture, to take a look at this is by an example. It works like a mathematical microscope. So if you're given a signal, like with 2 to the n samples, we say that this signal is at level n, we can project it down to the next coarser approximation level. And so we've lost some information. The signal now is like shorter. But on the right-hand side, we're capturing all the information that we lost. And we can repeat that again to another level, less information. But again, we're capturing the information that we lost on the right-hand side. And we can do that for a number of levels until, let's say, we stop at level j, where we have very little, a small amount of samples, just 2 to the power of j. And That approximation, together with all the details that we lost when going from the original representation, is what we call the DWT at level J. So how can we use this in cryptography, and in particular to the acceleration of large language model inference? Well, we're going to present two gadgets. One is lookup table compression, and the other one is a vast interval comparison, both based on DWT. And then we're going to explain how to combine them to actually model those nonlinearities, which are complex. And also, in particular, how to model GLU, which is one of the most famous activation functions in LLM. And I'm going to provide some numbers as well. So the first application is lookup tables. Whenever you're facing a very difficult function, you can always try to model it with a circuit, like a Boolean or arithmetic circuit. But another alternative, if that circuit is really large, which is the case for these nonlinearities, is actually to sample the function and to create a table that contains that samples, and that is the lookup table. And so this is a very generic and general approach. It can be used, for example, in FHE as well, but here we're focusing on linear secret sharing. So instead of linear secret sharing, if you want to evaluate privately that lookup table, which is public, meaning you want to obtain what its value is at some secret point A, you can go about it by using a secret shared description of a one-hot vector, which is a vector of all zeros except for a 1 at position A, and then do the inner product of that secret sharing one-hot vector against the lookup table. And you will obtain a sharing of the lookup table at position A. So, of course, in linear secret sharing, we are not usually handling, one-hot vectors or sharings of one-hot vectors. So how do you go from a sharing of A to a sharing of a one-hot vector pointing at A? One answer is to use preprocessing. So in preprocessing, you compute a one-hot vector pointing at some random point R, and you provide a double sharing. On the one hand, you share R, and on the other hand, you share the one-hot vector. And so you reveal R minus A, and that's a public shift that you perform on your one-hot vector, and now your one-hot vector is pointing at A, so now you can do the inner product against the lookup table and actually get the sharing that you wanted. The problem is that this sharing of the random one-hot vector is huge. It can be huge because it has an exponential number of bits. And that's why function secret sharing is used, because it actually can compress that, logarithmically speaking. So from a size of 2 to the power of n, you go to O(n), which is really interesting. But to decompress that vector, you have to run an eval algorithm that is exponential in the number of bits. And so that's the problem. You need to run a lot of PRG calls, a lot of pseudo-random number generator calls, and that's the reason why you have a problem with computational complexity. So we would like to explore a different alternative to that. The idea is that we want to replicate the same operations we're doing at level n at a level j that is coarser. Why? Because at level j, everything is shorter. Instead of working with 2 to the power of n vectors, now you're working with 2 to the power of j vectors, and j is smaller than n. So can we replicate the same? Well, actually, if you perform the hard DWT transform on a one-hot vector, you get also one-hot vector. It's shorter. The non-zero element is different, is r prime, but it's related to r. Also, the circular shift that we were doing at scale n, now we can also find an equivalent at scale j. Again, it's different, but it's related. And in doing so, we can now have a one-hot vector pointing at a prime, which again is related to a. So at this point, we could reverse the transformation and go back at level n, expand the vector again to make it 2 to the power of n samples. But instead of doing that, because we're interested in reducing computational complexity, we want to try and find if there's a way to do like a version of the inner product, but now at a scale j, so a smaller scale. The answer is yes, there is such an operation, which is guaranteed by means of Parseval's theorem, which establishes a relationship between the inner product of two signals at level n and the inner product of their approximation coefficients plus inner products of their detail coefficients. But we're going to forget about those inner products with detail coefficients and just focus on the ones with approximation coefficients, because compression is going to be good. So there's going to be some error, but the observation is that all the nonlinearities we are interested about, they are very smooth. They don't have abrupt changes. And the approximation coefficients, they act as low-pass filters, meaning they're going to capture that information which is smooth. Whereas the detail coefficients, they're going to capture the high frequencies which are non-existent in those signals. So they're going to be 0 or close to 0 anyway, and we can just forget about them and work with the approximation at level J. These are some results when we use this technique with the most important nonlinearities. For example, the first function is related to GLU. And when we use the approach of quantizing the lookup table, cutting the number of bits, we can have a representation for a certain length of 256 with certain error. But when we use this technique, DWT compression, we get it down to 36, and actually with a smaller error. The same happens for 1 over x. So we go from 1024 down to 68, again with smaller error. The same happens for sigmoid and for exponentiation functions. So in general, it's a very powerful technique. Actually, DWT compression is part of the JPEG 2000 standard for image compression. So there's no question why it works. But sometimes it's not enough because you work with, let's say, 64 bits, and even if you apply compression, you're going to end up with still very large lookup tables. So we're going to try and combine that with another approach, with another gadget, also built on DWT. You could, of course, use function secret sharing to further reduce the key, but we're going to do this other way. So, for example, the observation is that in GLU and many other nonlinearities, they typically have one interval where they're more interesting than on the rest. For example, here in GLU, between -4 and 4 is really interesting, is where the magic happens, but outside of this interval, it's like a ReLU. It's like 0 to the left, x to the right. So the idea is to use a comparison protocol, an interval comparison protocol, so that if we fall inside of the interval, we use a very high resolution representation using the DWT compression, and if we fall outside of it, we use the ReLU that we can build with a comparison. Or alternatively, we could also use lower resolution lookup table. The key observation to building this DWT-based interval comparison is that if you represent an interval at level n as a vector with all zeros except for ones inside of the target interval, if the interval meets some conditions, you're going to find a way to represent it very succinctly with just one non-zero coefficient at some level t. So you're going to have this very efficient way of working with the interval comparison, but just working with a one-hot vector, which is very short. But of course, this only happens when the interval meets some requirements, which generally is not the case. So that means we're going to have some randomness, which introduces the notion of a fuzzy interval comparison. The idea here is that we're going to relax the requirements of having a perfect interval comparison in favor of this fuzzy version, because this fuzzy version is going to be, it's going to have a smaller footprint in terms of the number of bits it requires to operate with. And the idea of this fuzzy interval comparison is that you have two intervals, actually. One is the target interval, and this protocol is going to return 1 whenever you fall inside of the target interval. And it has this outer interval, and it's going to return 0 when you're outside of the outer interval. But in between, you have these two fuzzy regions where the protocol sometimes is going to return 1 and sometimes 0. So you cannot really trust what happens inside of these two regions. Nevertheless, this is good enough for our purpose because we can fit the interesting part of our function to the target interval, in this case between -4 and 4. We can expand the high resolution description of this function to the outer interval. So yes, we're going to multiply by 3 the interval for which we need high resolution, but we're going to use the DWT compression in this, so it doesn't really matter much. And then outside of that, we're going to use, in this case for GLU, we're going to use the ReLU, which is built with a comparison, but in general, it could be another lower resolution lookup table. So we applied this to GLU just to see how it works and compared it to the best construction of GLU that is based on function secret sharing that is provided by Sigma. And the result is that Sigma is using function secret sharing both for the interval comparison, they're using a similar technique, as well as for the lookup table. So they're compressing all the lookup table with FSS. Whereas we are using both these WT constructions for the lookup table and for the interval comparison. And of course, we have PRG calls. That's one big difference. But another difference is that because we work at a level J that is smaller than the original level, we work with representations that are smaller, actually. So in terms of computational complexity, we don't have those PRG calls that cause the bottleneck. But also, in terms of bandwidth, the amount of information that we need to provide in pre-processing, we also have a reduction because we're able to work at this lower resolution scale. So in summary, we have seen that the top performers in linear secret sharing based private inference for large language models, they're all using function secret sharing, which is true that it makes some simplifications, like it's a two-party protocol, but it's really performant because it's able to shift what you typically find in linear secret sharing to be the bottleneck, which is communication complexity or round complexity, to computational complexity. And so the problem now becomes running these PRG calls. And we have seen MRA, which is multi-resolution analysis, and the discrete wavelet transform as is a theory well known in digital signal processing, but we've seen an application to cryptography. We've built two widgets or two gadgets. One is lookup table compression gadget. The other one is a fast interval comparison. So one is just shrinking the tables in general. The other one is focusing or zooming in some interesting parts of the signal to provide more resolution there. And what it turns out that these techniques do is to reduce the number of PRG calls. So it tackles this bottleneck with computational complexity that we have with function secret sharing. And it also reduces actually the key size that you need. So it's like a win-win in terms of these two parameters. And probably once you tackle the computational complexity, the next bottleneck is going to be probably the communication complexity. So it's good that we're also improving on that. And this technique, we have seen it for linear secret sharing. We think that it could have applications to FHE as well. We have seen it for large language models in AI, but we think that it also has applications beyond that. As long as your functions, the ones you're interested in, are smooth, then you will have this DWT compression property that will enable for a succinct representation of those functions in the form of lookup tables. And we've seen that we can also actually combine it with a function secret sharing scheme. So you could apply DWT compression to shrink it, to shrink the lookup table, and then you could apply FSS to even shrink more the one-hot vector representation that you get from the compressed lookup table. Thank you very much.
Questions from the audience?
Yeah. Thanks. Yeah, do you have a paper published somewhere? Or?
It's coming. We're working on it.
Coming.
It's coming, in short,
okay.
Yes.
All right. Okay. Thanks.
Any other questions? I have a question. So, like, does the noise matter at all? Like, when you do the approximation, or is it because you're working with LLMs that the noise does end up mattering for the final output?
So why does it smaller the noise?
Yeah. So, is it because you don't need exact computation here?
Yes, exactly.
Okay.
So yes, the premise is that you are allowed for a certain amount of approximation error that doesn't affect the model accuracy because it's AI, so it does tolerate certain error. And there's some measurements, derived from practical, implementations of this done by Microsoft in Sigma. It's around 31 ULP, so more or less 31 units of deviation from the exact value. And those are tolerable. And so we're working within those ranges. So that means that in principle, this shouldn't affect the model accuracy at all.
Got it. Thanks.